into trouble. If I could have a moment. Right. So, lambda calculus is, the compiler is much shorter, but it's also weirder because we've got more stuff to worry about. Right? The thing about functions, right? Lambda abstractions represent functions, is that they run in two stages, right? First of all, you've got to make a thing that represents the actual function, and there's going to have to be something that's not going to be doing nothing, right? And then sooner or later, some input is going to turn up for that function, and at that point, the function will actually have to do something. So we will have to have some way of representing how to store all of the bits and pieces that are going to be needed when the input to the function turns up. Right. So that's going to involve, remember when we did the dynamic semantics, we had a call by value version where we represented values for functions as closures, right? I mean, what do you need to know to be able to run a lambda term that has some free variables? You need to know the values of the free variables. When we arrive at a lambda abstraction, the reason you can't already evaluate the body of the lambda abstraction is that although you know all the free variables, you don't know the value for the bound variable yet. So you've got no choice other than to just pack up what you do know and wait for this value to arrive. So we're going to have to manufacture some means of representing environments and closures on the massive machine. And there, we are going to make use of the fact that the massive machine has a heap. And what we use a heap for is persistent storage of stuff that might stick around and get used any old time. And that's the other thing. You know, you got some values, they live in an environment, you don't know when they're going to be used. Life is not as easy as just keeping the values of the variables on the stack, because those values get packed up in closures and chucked around all over the place. So we're going to make use of the heap, and here's the plan. We're going to store environments. I mean, this is, again, a choice, and as ever, it's necessary to be consistent more than to make one choice in particular. But the plan is to represent environments as linked lists stored in the heap. So the way you build a linked list is you have a pointer into some heap location. So a linked list is made of cells. Each cell is built from 2 consecutive memory locations in the heap. And what do we put in them? We put some sort of value in the first of the 2 cells, and in the second of the 2 cells, we have the pointer to the rest of the list. So these cells the 2 cells here, these 2 cells have to be contiguous in memory. They have to be next to each other, so that the address of this one is 1 plus the address of that one. But the separate cells of the list don't have to be contiguous in memory at all, and indeed they can be sharing. We could have some other list down here that we also have a pointer to, and its tail could also be that cell. So there is at least some sharing. So the good news about the heap, the way things work in the massive machine, is that there's a special register whose job is to tell us the first available bit of heap memory, right? There's a thing called the free pointer, and the way we use it is to make sure that all of the heap space we've allocated so far is below the free pointer. So if we want to make a new cons cell, we can choose to make it at the place where the free pointer is currently pointing, and then we can advance the free pointer now that we've used a bit more heap. So the free pointer just goes up and up and up as we allocate more and more heap space. Okay, so that is going to give us a way of representing environments. We've got to be a little bit careful. We need some convention to make sure that we know which value in an environment belongs to which variable. Now, the way we can manage that is, I mean, we could try and store some representation of the variable name or something like that and go looking for the value that has the right label, but we can get away with just making use of the order in which the variables are bound. We know which lambdas we're under. If we can replace the way in de Bruijn index land, right? We might represent this sort of thing becomes, that's a pointer to that lambda, and that's a pointer back to that lambda. We could represent that by the number 0 and that by the number 1, telling us how many lambdas to jump over till we get to the one that bound the variable we're talking about. So that's the key thing, is that we can, every time we go under a lambda, its variable comes into scope. So it becomes the thing in position 0, and everything else moves along 1. So we're going to work with the position of a variable in the list of the variables we've seen so far, rather than the name of the variable. So that means when we have an environment, the most recent thing is the first thing in the list, and then this is the next most recent. So as the variables get less and less local, the values get further away from the beginning of the list. So if you think about it, that's a sort of sensible way to proceed. When we have a function, when we're building a closure, the value that's currently missing is the one that is for the most local variable, the variable we're just binding right now. Yeah? And what we need to do when the value of that variable turns up is complete the environment, which we can do just by gluing a new cons cell on the front of the list. Sorry, I said a Lisp word. These cells are often called cons cells after the Lisp operation cons. This data structure is basically the foundation of the programming language Lisp. And the operation to build a cell from a head and a tail was called cons in the 1950s, and it's still called cons now. I learned Lisp when I was a tiny child, and I correspondingly slip into its vocabulary rather easily. Okay, so we've got this idea that we're going to represent environments as these linked lists of values with the most local one nearest to us, and then working our way down the list for the less local ones. How do you think we might represent a closure? Well, what was a closure when we did it on paper? It was a pair of an environment and the term that we were going to evaluate when we get the extra value. So we figured out how to represent environments, but we're not going to store raw syntax of the lambda calculus in our compiled code. Terms are going to turn into code. So what we'll have is a code pointer that performs the behavior of that term, but it needs to be given a complete environment. And the reason we're building a closure is that we've got an environment with one thing missing. So what we need is, to make a closure, we need a pair of a code pointer and an incomplete environment. Okay, so that's how we're going to represent a function value as a heap allocated closure, which is made of const cells, and the first const cell is going to have a code pointer in the head, and its tail will be the incomplete environment that we're going to need to complete once the argument to the function turns up. So once the argument to the function turns up, we'll have all the information we need. We'll have the incomplete environment, we'll have the value needed to complete it, and we'll have the code that we need to run once we've built that environment. Okay, so how do we actually generate this code? Well, actually, yeah, first of all, let me just show you how you allocate a const cell, because we're going to be doing a lot of that. This code pattern is going to show up all the time. How you allocate a const cell? You say, in the heap, wherever the free pointer is, we want to put whatever the head thing is, whatever we're going to stick at the head of the sequence. In the very next cell in the heap, we put the tail. We store the old value of the free pointer. You can see now this register, RE, is pointing to the const cell in the heap. And then, of course, we've got to make sure that we protect that memory from being dumped on. So we better add 2 to the free pointer. So now we have a register which is pointing to our const cell in the heap, and the free pointer is ready, has moved past the memory that we used, ready to allocate the next const cell. So this is how to cons. Right. Everybody fine with that? So we're going to be doing that a lot. Okay, next thing we need to think about is what the deal is. So always with compilation you have to figure out when we're compiling code, what expectations are we relying on, what are we guaranteeing? So the code that corresponds to a lambda term is going to need to know the environment. And it's going to produce a value. So we need to decide where that is going to be. And today, for some reason, I've decided that. So the code for a term expects environment in the rest register. What else is it going to have to do? It's going to have to deliver a value. And perversely, perhaps, I'm going to say it delivers value also in the rest register. And it's going to, it might use the stack, but it's going to preserve the stack pointer. Because we're going to need to use the stack to store temporary information. The fact that we're building stuff on the heap doesn't mean we get out of using the stack entirely. So we've got a plan. Let's also think. We're not going to, so one good piece of news is that we don't need to allocate like local mutable storage or anything like that on the stack. So we're not going to have to fool about with the base pointer. We're not going to have to remember a frame height. All we have to do is make sure that we clean up after ourselves nicely and preserve the stack. So the compilation scheme is going to look like you get a term and you get an accessor, that's the exit, and we give back an accessor, which is the entry. So the same sort of deal. You get told where to finish, and you do a bit of compilation, and you supply, you give back where to start. So that much is the same as with imp. All right. Let's have a think about lambda, because actually that's the heart of the idea. Funnily enough, shocking, isn't it, to think that figuring out how to compile a lambda might be the important thing in how to compile the lambda calculus. I mean, it's not called the lambda calculus for nothing. Okay. So someone's going to give us something which looks like that. And we know our exit point. And that's going to be equal to some starting point where a bunch of stuff. Okay. This is a game of two halves. What we have to do now, remember when we evaluate a lambda, we give back a closure. So what we know at this stage, at our starting point, we know that the rest register contains the environment. And we know that that is the very environment that we want to pack up in our closure. So let's build a closure. So we use the recipe for consing that I just showed you. We build a const cell whose head is some code pointer, and we have to see what that is in a moment, whose tail is the environment, and that's in the rest register. And then we have to put our closure into the rest register because that's the value. And then we have to increment the free pointer by 2 so that we don't overwrite that lump of memory. We have just built a closure. No, that's the value we're going to give back. Right, we're done here. End of part 1. Commercial break. Exit via the shop. There's just one little problem. We haven't said what the hell code is. All right. So let's figure out what code is going to do. Well, maybe we'll think about that in a moment. So the code is the thing that's going to be run once we have the full-on environment, including the value of the bound variable. So we need to decide some stuff about how that's going to work. So maybe we can leave that as a cliffhanger and think about how to compile an application instead. Because that's the thing that's actually going to use whatever we put here. So let's just think about how that could possibly work, and that will tell us what to put in that block. So how do we compile an application? What order did I do it? We've got lots of choices. Okay. I'm going to do it proper call by value style. Right. We've got an environment in the rest register. It's going to be, that's the environment to be used both for evaluating the function and for evaluating the argument. And because we expect in general from our deal, right? This tells us that evaluating stuff trashes the rest register. So we're going to need to use the environment twice, once when we're evaluating the argument, once when we're evaluating the function. We better make sure that we don't forget it while we're doing the one so that we can still do the other. So step 1, push the environment onto the stack. Okay, what happens next? Now we're ready to evaluate either the function or the argument. I'm going to do the argument first. Right. Okay, so we evaluate the argument. Just check, is the environment for that argument in the rest register? Yes, it is. So now we know when we reach next that the value of the argument is in the rest register. So what we have to do, we know that we need to remember that value while we figure out what the function is, and we need to restore our saved environment. So what we have to do is swap the thing that we just got, that value, we need to save it on the stack and recover the environment that we stored on the stack. So we need to do the traditional dance of get the thing that's on the top of the stack, that's at SP minus 1. Overwrite it with the thing we still want to remember. So that's just a swap. Swap the thing in the rest register with the thing on the top of the stack. So now we know that we've got the environment back in the rest register. We're ready to evaluate the function. Yeah, this is quite a long story. I'll zoom out. Okay, so when we reach go, what do we know? We know that we've got the value of the argument on top of the stack, and we know the rest register now contains the value of the function, which had better be a closure. So what do we need to do? We need to build we need to grab hold of the code pointer, and we need to complete the environment. Let's get cracking. So I'm going to grab the code pointer. Remember, the rest register points into the heap to a const cell. So this is getting hold of the thing that's in the head of the const cell. Meanwhile, the incomplete environment is in the tail of that const cell. Okay. Next thing I have to do, that's the incomplete environment, I have to complete it. Which means I have to allocate a new const cell. What am I going to put in it? I'm going to put in it the value of the argument. That's what's sitting on top of the stack. The tail of that const cell is going to be the rest of the environment. Oh, that should be +1. The rest of the environment. Then I need to, now that I've done that, need to get the completed environment into the rest register and update the free pointer. So can you see this? That's the incomplete environment, and this is now the complete. That's the code pointer. Right. So now we have one last little bit of thing to think about, which is how do we make sure, so we're ready to call the code pointer, except that we've got to make sure that we end up at the end. So we have to find a way to tell that code how to finish. And what do we usually do when we're calling subprograms? We store the exit route on the stack. So here's the game. We overwrite, we store our own exit address on the top of the stack, and then we exit via the first register. Isn't that wacky? So the stack remembers where we've got to finish up. And we just jump to the code pointer we extracted from the closure. So that should give me just enough time and space to finish off the mystery. We notice also that we have incremented the stack pointer right at the beginning. We put something on the stack. And we've got to make sure we restore the stack in the end, which means that it's going to be the responsibility of the code at the code pointer to pop the stack. But it's actually getting something useful on the stack, namely the return address. So it probably wants to do that anyway. So, now that we've seen how this code here is going to get called, let's figure out what it consists of. If I can only remember. It's actually the code that you get by compiling T with an exit point done, except that as we did with new variables in imp, we have to locally update the symbol table. So we locally bring x into scope. I'm mapping it to 0. It doesn't actually matter what I map it to. What matters is its position in the symbol table. That's going to tell us how far along the environment to go. Then that is going to exit via done. And what is done going to do? What is there left to do? We've actually computed the value of the function body. The only part of the deal we haven't kept is twofold: to tidy up the stack and to exit via the original end marker. And we can do that in short order. We pop the stack, and we know that what was on top of the stack is exactly the original end marker, the original end address. So we exit via what was on the top of the stack. So here, wherever I put it, here we saved our eventual destination on the stack. That's the return address. And here we actually end up going there. And we've maintained the stack height invariant. So this is kind of funny, disjointed thing that's missing some semicolons, where this program doesn't actually call this program. It just stores the address of this program in a data structure. And then some other thing puts the pieces together. So I'm not going to write, this file with this compiler full of comments lives in a file in a repository. I'll make sure you get your hands on it. So just to say how we compile variables, we can look up the position of the variable in the symbol table. That tells us how many steps along the linked list to go before we find the value that we want. So we just do that with a loop. We get that number, and we just loop that many times, pulling that many cells off the linked list that is the environment before we grab the value we want. But I think it was important to show you, lambda and application as the essence of what makes lambda calculus work. And so it's code pointers stored in closures by the code for lambda, unpacked and actually jumped to by the code for application. And yet more of this is how we really reify the, code is data. We really do take code pointers, pack them up in data structures, chuck them around, unpack them, jump to them when necessary. Of course, if you accidentally, in this situation, put a number in a function position, then that number will be taken as the heap address of some closure. So you've got some random pointer into the heap that is just meant to be a number. And then whatever is stored in the heap at that location, that's going to be taken to be a code pointer. And we're going to jump to it. So this is how come if you don't have a sensible type system for your lambda calculus and you want to compile it vaguely sensibly, segmentation fault is quite likely. So all of this, the fact that any of this fits together really relies on, we're trusting here that function values are indeed these closure things, and we know that what we've got in our hands is a code pointer, because we're just picking some random value out of the heap and jumping to that location in the generated code. So we better get these things to fit together properly. Okay, I better stop there. I better put the box at the back of the room. And thank you very much. That's compiling the lambda calculus.